Hi, my name is Sterling Quinn, and I will be presenting the implications of serverless application flow control. I was advised in this project by Dr. Wes Lloyd at the University of Washington, Tacoma. In this project, we attempted to quantify how different choices in serverless application flow control affect the cost and performance of your overall application. We use some standard AWS services in this project. We also use the Serverless Application Analytics Framework, which is a project developed at the University of Washington, Tacoma, that allows developers and researchers to examine the performance of their serverless functions by looking at operating system metrics. For this project, we examined the following data processing pipeline. It consisted of a transform step where data was loaded from S3, transformed, and re-uploaded to S3. A load step where data was loaded to a SQL database, and a query step where that data was queried. Our first method of flow control is going to be referred to as the VM client. This is where a cloud client performed the orchestration. Our second method will be referred to as the state machine. This is a AWS step function implementation where the cloud provider manages the transitions and the data passing, and we are billed per transition. This is an asynchronous method, so to determine when the pipeline finished running, we'd poll for completion. Our third method is the microservice controller. This is where a fourth serverless function performed the orchestration of the other three. This suffers from the double billing problem where you're paying for the running controller at the same time as paying for the worker functions. Our reason for including this pattern was we were wondering whether running the controller at a low memory setting would be cost effective since the work of the actual controller is quite simple. Our fourth method is event-based triggers. The event in this case is an S3 upload event, which would trigger the next step in the pipeline. This is another asynchronous method where we'd poll for completion of the pipeline. We look at the following metrics: function runtime, pipeline runtime, and latency. Pipeline runtime, which is from the start of the first function to the end of the last function, and latency, which is the transition time, are the most important in this presentation. In considering the overall performance, we performed an experiment where we examined the runtime for a variety of different data sets. Considerations and overall performance: the event-based triggers method required additional worker function runtime because that method of flow control does not provide payload passing, so we had to do additional downloads to get the payload. Here's a graph examining our results from this. You can see that the event-based triggers method was the slowest, and that performance penalty was a pretty small overall penalty at a large data set size, but a large penalty at the smaller data set sizes. We also look at the cost of your choice here. So we should remember that there was additional worker runtime for event-based triggers, that asynchronous methods have constant transition costs, and that synchronous methods you'd be paying for the running resource as throughout the runtime of the pipeline. See our results here that paying for that resource is reflected in the cost, as those synchronous methods scale much faster in cost as the overall pipeline runtime increases with rows of data. So your question here would be, what is the best flow control pattern? For us, it seemed to be the step functions implementation. This is an AWS offering specifically designed to solve this problem, and it did perform the best. Event-based did come with performance and development penalties. The client would be appropriate. The VM client would be appropriate for smaller use cases. And while we were able to decrease the cost of the microservice controller by using a low memory setting, it was still the most expensive method.